Hello and welcome to Electro Nerds Academy. In this video, we'll learn 3 simple ways to measure water level using an Arduino. Let's start with the first method, using a float switch. Float switches come in 2 common types, the magnetic float switch and the ball-type float switch. The magnetic float switch uses a reed switch inside and a magnet on the float. When the tank is empty, the float stays down and the reed switch remains open. As the water level rises, the float moves upward with it, closing the reed switch. This type of float switch usually comes with 2 wires, one for common and the other one for normally open contact. The second type of float switch is the ball-type float switch. In this switch, instead of a magnet, there is a small steel ball inside. When the water level rises, the float tilts upward, the ball rolls and opens the contact. When the water level drops, it rolls back and closes the contact. This type of float switch usually comes with 3 wires, common, normally close, and normally open contacts. Now, let's make a simple Arduino project using a float switch. In this setup, when the tank is empty, a buzzer will sound to alert us that the tank is empty. When we press the push button, the pump turns on and keeps running until the tank becomes full. Once it's full, the buzzer gives a short beep, and the pump turns off automatically. Now let's look at the circuit connections. We're using a 12-volt water pump connected through a single-channel relay module. The positive wire from the 12-volt supply goes to the common terminal of the relay. The normally open terminal connects to the positive wire of the pump, and the negative wire of the pump goes directly to the power supply ground. The relay module is controlled by the Arduino. VCC of the relay connects to the 5 volts pin of the Arduino Uno. GND goes to ground pin and the signal pin connects to digital pin 8 of the Arduino. The push button is connected between Arduino pin 7 and ground. Next, we have our float switch. We're using a magnetic float switch, which has 2 wires, one common and one normally open. The common wire is connected to the GND pin of the UNO, and the normally open wire is connected to digital pin 9 of the Arduino. Finally, we connect the buzzer to pin 10, with its negative terminal going to ground. Now, let's move on to the code. We'll start by defining the pins connected to our components. The push button is connected to pin 7, the float switch is connected to pin 9, the relay module is connected to pin 8, and the buzzer is connected to pin 10 of the Arduino Uno. Next, we have declared 2 Boolean variables, button state and float state, to store the current states of the button and the float switch. We have also declared another Boolean variable, pump running, to keep track of whether the pump is currently on or off. In the setup function, we'll configure all the pins. The button and float switch pins will be set as inputs with internal pull-up resistors enabled. This means they will normally stay high and only go low when activated. Next, the relay and buzzer pins are configured as outputs. Initially, we'll keep the relay pin high so that the pump remains off because our relay module is active low. It only turns on when the Arduino sends a low signal. Similarly, the buzzer will be kept off at startup. Now in the loop function, we'll continuously read the states of the button and the float switch and store them in the button state and float state variables. After that, we'll use 3 if statements to handle different situations. First, when the tank is empty, second, when the user presses the push button, and third, when the tank becomes full. Let's go through each one step by step. Initially, the tank is empty, so the float switch pin remains high due to the pull-up configuration, so the float state variable is also high initially, and since the pump is off, pump running variable is false. This makes the first if condition true. As a result, the buzzer beeps for 300 milliseconds, pauses for 500 milliseconds, and repeats, serving as a reminder that the tank needs refilling. When the user presses the push button, the button pin becomes low. As a result, the button state variable becomes low. And since the pump is still off, pump running variable is still false. Therefore, the second if condition becomes true. The code then updates the pump running variable to true, sends a low signal to the relay module to turn on the pump, and stops the buzzer. A short delay is also added to prevent button bounce. Now that the pump is running, the water level starts to rise. When it reaches the top, the float switch changes state from high to low, indicating that the tank is now full. This triggers the third if condition. As a result, the buzzer sounds for half a second as an alert, and the relay is set high again to turn the pump off. And finally, the pump running variable is reset to false, returning the system to its initial standby state. Now let's upload this code to our Arduino. After a successful upload, note that initially the tank is empty, so the buzzer starts beeping to remind the user to fill it. Once you press the push button, the buzzer stops and the pump turns on to fill the tank. When the tank becomes full, the float switch detects it, the buzzer gives a short beep, and the pump automatically turns off. The entire process then repeats automatically whenever the water level drops again, providing a simple, automatic, and reliable water level control system. The second method we'll use to measure water level is with an analog water level sensor. Unlike a float switch, which only tells you if the tank is full or empty, this sensor gives a continuous voltage output, so you can see exactly how much water is in the tank. The circuit diagram of this module looks something like this. At the heart of this sensor is an S8050 NPN transistor and 10 interleaved copper traces. 5 traces are connected to positive 5 volts through a 100 ohm resistor, and the other 5 connect to the transistor's base. When water bridges these traces, its conductivity allows a small current to flow into the base, turning the transistor on. This lets a larger current flow from positive 5 volts to ground through another 100 ohm resistor, raising the output voltage at the sensor's out pin. The more water touches the traces, the greater the conductivity and the higher the output voltage, producing a true analog signal proportional to the water level. If we look at the actual module, we can see 10 interleaved copper traces. One set of 5 traces is connected to the positive 5-volt power supply through a 100 ohm resistor, while the other set is connected to the base of an S8050 transistor. The module also includes a power indicator LED and has 3 pins: signal, which provides the analog output, VCC for connecting the 5 volts power supply, and GND for ground. Connecting this sensor to our Arduino is simple. We'll connect the signal pin of the sensor to analog pin A0 of the Arduino, GND to ground, and instead of connecting VCC directly to 5 volts, we'll connect it to digital pin 7. This way, Arduino can power the sensor only when needed, preventing corrosion from constant water contact. Now let's take a look at the code. We'll start by defining 2 pins, pin 7 to power the sensor and A0 to read its analog output. In the setup section, pin 7 is set as an output pin and kept low at first, so the sensor stays off until needed. We also start serial communication at 9600 baud to view the readings on the serial monitor. Inside the loop, we turn the sensor on by setting pin 7 high, wait a short moment for it to stabilize, then read the voltage from pin A0 and store it in a variable called level. Right after reading, we switch the sensor off again to prevent corrosion. Finally, we print water level reading on the serial monitor. After a 1-second delay, the process repeats, giving a live water level reading every second. Now let's upload this code to our Arduino, and after a successful upload, we will open the serial monitor. When the sensor is completely dry, it will show a value of 0. When the sensor is partially immersed, the reading increases to around 420. When the sensor is fully immersed, the reading goes up to 520. At this point, there are 2 important things to remember. First, the sensor's readings can vary depending on the type of water you're using. Pure distilled water doesn't conduct electricity well because it lacks minerals. It's actually the dissolved minerals and impurities that make water conductive. Second, this sensor is not meant to be fully submerged. Only the lower part with the exposed copper traces should touch the water. Keep the upper circuit area dry to avoid damage. Now let's make a simple water level indicator that lights up LEDs based on how much water is detected by the sensor. We will connect 3 LEDs, red, yellow, and green, to digital pins 2, 3, and 4 on our Arduino via a 220 ohm resistor, whereas the negative terminal of all LEDs will be connected to the GND pin of the Arduino. Each LED will light up depending on whether the water level is low, medium, or high. Now let's look at the code. At the start, we define pin 7 to control the sensor's power and analog pin A0 to read the voltage from the sensor. Next, we define 3 digital pins, 2, 3, and 4, which are used for the red, yellow, and green LEDs that indicate low, medium, and high water levels. 2 threshold values are also defined, one for a low level, 420, and another for a high level, 520. We get these values from our previous example. These can be adjusted depending on how your sensor behaves when the water level is low and when it is high. In the Setup section, we initiate serial communication with a 9600 baud rate. The sensor power pin and the 3 LED pins are set as outputs. Initially, the sensor is turned off by writing a low signal to pin 7. Inside the loop, the Arduino first turns the sensor on by setting pin 7 to high and waits for 10 milliseconds so the sensor can stabilize. It then reads the analog value from A0, which represents the water level. After taking the reading, the sensor is immediately turned off again to prevent corrosion. Next, the program checks the reading and determines the water level status using a bunch of if and else if statements. If the reading is 0, it prints water level empty on the serial monitor, and all LEDs are turned off. If the reading is less than or equal to the low threshold, it prints water level low on the serial monitor and turns on the red LED. If the reading is between the low and high thresholds, it prints water level medium and turns on the yellow LED. If the reading is above the high threshold, it prints water level high and turns on the green LED. Finally, the Arduino waits for 1 second before repeating the process, giving you updated readings every second. Now let's upload this code to our Arduino. And after a successful upload, we will notice that when the tank is empty, all LEDs are off. As the water level rises, the readings increase, but they are still below the lower threshold, so the red LED turns on. When the water level increases further and falls between the two thresholds, the yellow LED lights up. And when the tank is completely full, the reading goes above the upper threshold, and the green LED turns on to show the tank is full. The third method we'll use to measure the water level in this video is by using an ultrasonic sensor. So, let's talk about a few advantages of using an ultrasonic sensor compared to a float switch or an analog water level sensor. First, unlike the other two sensors, the ultrasonic sensor doesn't come in contact with the water at all. This means there's no risk of corrosion, giving it a much longer lifespan. Second, it works with all types of water: clean, dirty, conductive, non-conductive, or even chemically treated. And third, there's absolutely no risk of electrolysis, short circuits, or current leakage. For this project, we'll be using the HC-SR04 Ultrasonic Sensor. We already have a separate video explaining how to interface the HC-SR04 with an Arduino, so make sure you watch that first if you haven't already. Now, let's replace our analog water level sensor with the HC-SR04 module in the previous circuit. To do this, we will connect the trigger and echo pins of the sensor to Arduino pins 6 and 7. Then we will connect the VCC and GND pins to the 5 volts and ground pins of the Arduino Uno. Now that our circuit is complete, let's look at the necessary changes we need to make in the code. At the top of the code, we've defined the Arduino pins connected to the trigger and echo pins of the ultrasonic sensor. The LED pins declaration is the same as before. In the Setup section, we configure the trigger pin as an output, the echo pin as an input, and all LED pins as outputs. We also start serial communication to view the readings on the serial monitor. Inside the loop, the Arduino first sets the trigger pin low to clear any previous signal. After a short 2 microsecond delay, it sets the pin high for 10 microseconds and then back to low again. This sends an ultrasonic pulse that bounces off the water surface. The Arduino measures how long it takes for the echo to return using the pulse-in function and stores that value in the duration variable. We then convert this time into distance by multiplying it by 0.034, which is the speed of sound in centimeters per microsecond. Then we divide the result by 2, since the sound travels to the water and back. Dividing by 2 gives us the distance in centimeters from the sensor to the water level and not back to the sensor. The reading is then displayed on the serial monitor, and based on this value, the Arduino decides which LED should turn on. If the distance is more than 6 centimeters, the red LED lights up, meaning the tank is low. Between 4 and 6 centimeters, the yellow LED turns on for medium level. And below 4 centimeters, the green LED comes on, showing the tank is nearly full. You can adjust these threshold values according to the size of your tank. After that, our Arduino waits for a second and repeats the process, giving you live water level updates. Now, let's upload the code. Once the upload is complete, we'll begin with an empty tank. All LEDs will be off, except for the red one. As the water starts to fill, the sensor readings change. When the distance between the sensor and the water surface decreases to between 4 and 6 centimeters, the yellow LED turns on. Finally, when the tank is full and the distance drops below 4 centimeters, the green LED lights up to indicate a full tank. So that's all for this video. We hope you find it helpful. Be sure to check out our channel and visit our website for more content like this, and we will see you in the next one.